Hello everyone. This series deals with some basic concepts relating to electrical machines. In the first presentation, we will revisit Amperes Circuit Law and magnetic circuits. This will include self-leakage and mutual inductance definition and calculations. The second presentation introduces some useful magnetic circuits. These circuits, some of them will employ concentrated coils on salient poles, and others will employ distributed windings. In the third recording, the concept of rotating magnetic field will be introduced. Thereafter, a short presentation concerned with generation of EMF will be given. The production of torque due to interaction of two magnetomotive force is the topic covered in the fifth recording. And during the fifth recording, we will, in general term, discuss how torque is produced in DC, induction, and synchronous machines. Thereafter, I'm planning a number of individual presentations. Each will deal with individual type of machines, DC, synchronous, and induction, the conventional machines. Then we will move into machine control, that's basically drives, and after that we will conclude with some other special types of machines. So enjoy the series and good luck. Now, if we consider an infinitely long wire carrying current I in free space, by symmetry we'll know that the magnetic field will be circles. Well, if we go back to the early 1800s, it was observed that current carrying conductors will behave like magnets. If you have two conductors with current in them, they will either attract or repel. So that was observed in the early 1800s, and then afterwards it was quantified, and now we know how to calculate the magnetic fields. Anyway, by using the right-hand rule, we can determine the relationship direction-wise between current and magnetic field. And what is the right-hand rule? You should remember from physics that if the current is the direction of the thumb, then the magnetic field lines will be like the fingers. In this case, if the current is going as shown, like the thumb, then like the fingers, so that will be the direction of the magnetic field. And from symmetry, there will be concentric circles, circles, getting weaker and weaker as you go away from the conductor. Later on in the 1800s, the relationship between electric current and magnetic fields was quantified in Amperes Circuit Law, which basically states if you integrate H along a closed contour, H dot dl, that will equal to the sum of all the currents enclosed within that particular contour. Before we move on to calculations, the right-hand rule gives the relationship between current and magnetic field, or if the current is in circles, then the magnetic field will be as the direction of the thumb. For example, if we look at this here, if the current is going like this, it will be like this, and that's enough. So you can see if you apply the right-hand rule, will give you the flux lines. We'll use the dot and the cross notations. Now the dot here indicates current or an arrow coming out of the paper, and if you remember the cross notation, this will indicate a vector going into the paper. This represents the end of the arrow, the cross. So we use the dot notation. This is now the current I. The circles will be like that. We take a point at a distance A away from the current carrying conductor, and a small angle delta theta. This length of the arc, will be the radius, the length of this arc, we call it delta L, equals the angle, which is delta theta, multiplied by the radius, which in this case is A. So to apply Amperes Circuit Law, we will integrate from theta equals to 0 to go all the way around. That will be 2 pi HR d theta. Actually, R here is A, and that will give you H at point A equals 1 over 2 pi A ampere per meter. The relationship between H and the flux density B is mu naught, where mu naught is the permeability of the free space. So now we have considered the magnetic field due to an infinitely long current carrying conductor, and we were able to calculate it. This is the case we considered earlier. We could have got exactly the same results if instead of current I here, we had N conductors, each carrying I over N, because what matters is the total current enclosed by the contour, and that's what's written here. Generally, we will use the current enclosed, the sum of all the currents enclosed by a contour. We call them magnetomotive force acting on the contour. We will call it F. And generally, in this particular case, we had our magnetomotive force, the force that is creating the magnetic field, is I. It could have been N conductors, each carrying I over N. Could have been anything else. Generally, we'll call it F, where F is the MMF, or magnetomotive force. Now, we bring a tube, an iron tube, and place it around the current carrying conductor. The flux density here, BA, will be much higher. Why is that? H will be the same, but B is mu R, mu naught. Mu naught is the permeability of the free space or air. Mu R is the relative permeability of iron, and if the iron is not saturated, mu R will be very large, several thousands, and we conclude from that in iron, very low values of H give us large values of B. And if we actually change the position of the current here and we move it a bit to the left or a bit to the right, the flux density in the iron is not going to change much. So the flux density in the iron is largely independent of the position of the current. Well, infinitely long current carrying conductor and infinitely long tubes are not a realistic proposition. So now we will look at some practical magnetic circuits. We will take something very simple, and then we will start modifying the simple shape we're starting with until we get to the end towards a typical shape of laminations that are used in electric machines. The main reason for this logic of the presentation is to show you that we're starting from very basic principles. Engineers start from very basic principles and end up building and creating and designing products. So we will consider this magnetic circuit. The cross-section area of the iron is as shown. I've chose mu R for the iron at certain value. Actually, I'm just playing with the numbers to end up with very simple numbers to manipulate. This is not a typical value. And if we have a coil of 50 turns and carrying a current of 1 amp, if you apply the right-hand rule, the current in the coil is going this way, so the flux lines will go like that. And I will assume that the length of the average length of the path, the flux path in the core is 0.5 meter. Again, I'm choosing numbers to give me, to ease the calculation. You will see that in a second. We look at this red flux contour. The magnetomotive force that is acting on this flux contour is the total current enclosed by the contour, and the total current enclosed by the contour is 50 turns multiplied by 1 amp, so it's Ni. Apply Amperes Circuit Law. F is Ni, and H.dl, we know L is 0.5, and they will give you H is 100 amp per meter. From that, B is mu naught mu r H, and here is my mu r. This is the mu r, and will give you a nice figure, 1 Tesla. Tesla is the units of flux density, or vapor per meter square. Vapor is the unit of flux, meter square is the unit of the area. From that, the flux is, the flux phi is flux density multiplied by the area perpendicular to that flux. B is 1, A is 10 meters, well, 10 actually centimeters square. So let me just remove this. So in meter, the 10 centimeters square be 10 to 10 multiplied by 10 to the minus 4. It will give me 1 milli vapor, or 1 10 to the power minus 3 vapor. So that's the flux phi. Why did I go for the concept of magnetomotive force? Because now we have something similar, treatment similar to electric circuits, and I believe you all should be more comfortable with electric circuits. So we have phi is B multiplied by A, that's B is mu H, H is F over L, and you end up with phi is F, magnetomotive force multiplied by this. Rearrange it, we end up with the flux phi is the magnetomotive force F divided by the reluctance, where the reluctance, I showed the reluctance as L over mu A. So in electric circuits, you have the voltage, or EMF, electromotive force, applied on a resistance R. The current I goes in a closed loop, and Amperes circuit, well, not Amperes, Ohm's law is V, I is V over R. Magnetic circuits, with using this equation, we can say we have magnetomotive force, in this case is Ni. It derives a flux phi across a reluctance R, and the equivalent relationship here to Ohm's law is phi is the magnetomotive force over the reluctance. This will enable us to treat magnetic circuits in the same way we treat electric circuits. But where did I get this from? I actually got this from Amperes Circuit Law. So this Amperes Circuit Law formation and the magnetic circuit concept are the same thing. It's a mathematical manipulation. Now we consider a core as shown, but I cut a small air gap. The air gap is 5 millimeters compared with the flux path in the iron, which is 300 millimeters, just to show that this is very small. But let's see what effect this small air gap has on the value of the flux. We calculate the reluctances. The reluctance of the core is the length of the core divided by mu naught mu r, area of the core. Give this value. The reluctance of the gap is the length of the gap and here mu r is 1, so it's a mu naught, gives us this value. Straight away you can notice that the reluctance, magnetic resistance to the flow of flux due to the 5 millimeter air gap is much greater than the reluctance, the resistance to the flow of flux in the iron path. Well, let's look at the magnetic circuit equivalent. F, phi, RC, we have two, this reluctance in series. Consider these two reluctance in series, calculate the flux, get 9 10 to the minus 4 vapor. If we ignore RC, the core resistance, the 300 millimeter, we end up with the same value. What we conclude here is, if the iron is not saturated, because the iron core has very high permeability, the reluctance of the iron will be very small. And in most of our calculations in electric machines, we can ignore, in the first instance, ignore the reluctance of the iron. This is like electric circuits when you have cables connecting an electric source to a load. When you're calculating the current, you don't take into account the resistance of the cable. Why? Because you know the cable have resistance, electric resistance, but it's very low compared with the resistance of the load. This is similar situation we have. We use the iron core here to carry the flux, but this flux is supplied to the air gap, which is the highest reluctance by far in the circuit. In other words, we can assume that the magnetomotive force Ni is acting on the air gap approximately. In this case, the integration of H dot dl will be H multiplied by G. This part here is the integration of H dot dl. Approximately will equal to H multiplied by G. Ignore the rest of the part of the integration. H will be Ni over G, and B will be mu naught, because it's air gap, Ni over G. And this will give us readily a very close but reasonably accurate value of the flux density in the air gap due to magnetomotive force given by Ni. We know now what reluctance is. Now we consider inductances. Inductances are associated with magnetic fields, and you would recall seeing them in equivalent circuits of electromechanical devices. Also, any of you who did power electronics would come across situation when we say we use an inductor, or even in filters and low signal electronics use inductors. Terms such as self, mutual, and leakage inductances are used, but what do they mean? We consider here a three-turn coil. What I'm going to introduce you now is to the term flux linkage. So we consider this three-turn coil. I'm just expanded it, and we look at the current. If the current is I going as shown in red, then apply the right-hand rule. You will find that the flux, let me just apply the right-hand rule again, going this way. Well, yeah, the flux lines will be as shown. You can see that the first turn here is linked by 1, 2, 3, 4 flux lines. And the turn at the end similarly is linked by 4 flux lines. The turn in the middle is linked by 1, 2, 3, 4, 5, 6 turns. So flux linkage is total flux linkage. You look at the flux that is linking every turn of the coil. The first turn is linked by 4, the middle turn by 6, the last turn by 4. So total is 14, and that's actually 14 vapor turn. That's the units of flux linkage. Definition of the self-inductance, L, is flux linkage over current. And for self-inductance, the flux linkage is caused by a current in the coil itself. Now, if all the turns of the coil were linked by the same number of flux line phi, so if all the turns were linked by phi, then lambda will be n phi. That's approximate. And you'll find in many books and equations, they just consider n phi as the flux linkage. That is not the general case. Now we know what the self-inductance is. Let's look at mutual inductance. What we have a coil here, coil A, excited with current. That current produces flux lines, and these flux lines are going like that, and of course they all go in closed contours. Then we bring this coil on the left. We bring this coil here to the proximity of coil A. This coil now is linked by flux generated by coil A. So these flux lines in the middle here, they link both coils. So these are mutual flux. If our aim was to introduce good magnetic coupling between the two coils, then our aim would have been to increase the mutual flux, make the coupling of the coils very, very large. If you look at flux lines like these are not linking, these are not mutual, these are not linking the coil, the second coil, and we call them leakage. You have to remember, leakage, you define leakage, you have to define a flux path. For example, if you have a pipe carrying water from A to B, any water that is leaked in the way that doesn't reach B is leakage water. If your aim here is to create flux in coil A that links coil B, any flux that doesn't link coil B, then it's leakage. So leakage flux has to be defined on a circuit. Anyway, this is an introduction to what is self-inductance and what is mutual flux and inductance, and what is leakage flux, and of course every flux component is associated with the corresponding inductance. We look at the self-inductance of a coil now. This is a coil. For a compact coil like this, the likelihood of all the turns being linked by all the flux lines is higher than if you have a long coil. Anyway, this coil is represented by this magnetic circuit and the flux line as shown. Then you can define L. We know L is lambda over I. You can use the equivalent magnetic circuit. This is the magnetomotive force, and the flux goes around. Again, back to this. If we assume all the flux lines link all the coil, lambda will be n phi. But from here, phi is F over R. F is Ni over R. That will give you N squared. I will cancel I. It will give you inductance N squared over R. Remember, R was the length of the magnetic path over mu naught, mu R, whatever, A. So this depends on the dimension. This depends on the parameters of the coil. So actually, all inductances are function of the geometry of the magnetic circuits. So this shows that the self-inductance is n squared, the number of the coils turns, divided by the reluctance. And here we are assuming that all the flux lines phi link all the coil turns. Now we are going to start with some magnetic circuits with air gap leading to the typical magnetic circuits used in electric machines. So I have a large air gap here and two salient parts. Each part carries Ni, N turns carrying current I. If you apply the right-hand rule, you will find that the flux is going down here and going there. So this surface, the flux will be going out. This surface, the flux will be going in. We define a surface that is emitting flux as north pole and the surface that is receiving flux as south pole. The total magnetomotive force applied on the air gap is 2Ni, and you can find B gap is mu naught 2Ni over G. What will happen now is I'm going to introduce some curvature. Didn't change much of the geometry, provided that the areas are the same. I inserted a cylinder here, an air cylinder. I tried to keep this air gap at the top and the air gap at the bottom. When you add them up together, you end up with the same air gap. The flux lines will first we insert the coils. We put the coils like that. We end up with the flux line like this. Of course, they are not just like that. They close around themselves, so the flux line will behave like this. You have to remember here that the flux line enter the iron and leave the iron perpendicular to the surface. And if the surface is a curvature, then these flux lines will be radially oriented. So this configuration here, we can see how the flux is behaving, and we can say, oh, this is now the flux is going out of here, so that's north, and it's going into this surface, so this is south. So we call this a two-pole arrangement. The previous configuration was a two-pole machine. A four-pole configuration is like what is shown. Again, the flux lines will enter and leave the iron perpendicular to the surface, and they go in a closed line. For example, this flux line will go something like that, and then here it will cross, and here it will cross radially, and here it will do something like that, and this one will go this way and this way. So the flux lines will be as shown, and if we travel across the air gap from this point and going clockwise, we will see somewhere here there will be no flux. Somewhere there the flux will be substantially constant, and here it will go zero. The flux will be pointing in one direction, and then it will reverse. So the distribution of flux density will be as shown, and let's follow it. Let's consider at point A. Point A here, it's between poles, the flux is zero, and I will move clockwise, so I'm moving this way. As I move this way, the flux will increase and the flux density will increase. Then between under the pole face, the flux will be substantially constant. So point B here, midpoint, it's constant. This will continue to somewhere here. And I say I can see the flux. If I'm moving this way, the flux is coming towards me. Coming towards me, I called it whatever, one direction, let's call it north. Then, and carry on moving to point C. Point C is midway, so the flux lines, no flux lines, the flux density is zero. Going for, again, moving clockwise, I will find that the flux is going away. This flux is going this way, going away from me. So it's opposite to what it was under this surface. We just reverse its direction. it will be substantially constant between the edge of this second pole to the third. And when I reach this point here, it will go 0 again. Then the same cycle will be repeated. We call this north-south. That's flux going in one direction. This is going in the other. We can reverse them if you like, but the convention is if the flux is going out of a surface, it's north. If it's going into a surface, it's south. Anyway, that's the flux distribution. And if you calculate it, we'll talk about this in a second. We'll just actually say, if we ignore the reluctance of the iron, and I showed you a couple of slides earlier, justification to this. You remember the case when we considered a flux path in the iron, which is 300 millimeter, and the air gap was 5 millimeter, and we found that if we ignore all the reluctance due to the iron, which has very high, several thousand of relative permeability, we found that the flux calculations will not be affected too much by ignoring the reluctance of the iron. If we ignore the magnetomotive force required for the iron parts, i.e. we assume mu r for the iron is infinity, we end up with the expression, the maximum flux density here is mu naught ampere turns per pole. Every pole has n turns, sorry, n, this is not n, this is scribble, n turns carrying current I, divided by the air gap length, and the air gap length here is G. So this is a very simple expression. Doesn't matter how complex the shape is. This is a 4-pole. The previous slide was 2-pole. You can extend the geometry to any number of pole pairs. And you can use the simple expression to calculate the flux density, the maximum flux density in the air gap. Another configuration that appears in the machine is this one. It's an inversion of the previous one. Now we have the poles are on the rotor. Again, flux lines go in closed circuit, so it will be like this. The radial in the air gap, and you will find that the flux out of this surface and into this surface, and here the flux lines will be doing something like that. If you follow the air gap, you will find the distribution is as shown, and again the flux density, the maximum value of the flux density is mu naught ampere turns per pole divided by the air gap length. Well, so far we considered the cases where magnetic field was produced by using a winding that is concentrated. And some machines, we need to distribute the winding. Why we need to distribute it, we'll come to that in a second. So the other type of construction that appears in electric machines is the distributed winding. And the distributed winding can be introduced by considering this cylinder, and the cylinder has one coil side going this way, other coming the other side. If this is the current, the direction of the current, then the flux will be upward. Anyway, to make it simpler to follow, we use a 2D sketch, and here we have the rotor. This is an arrow going in, yes, that's current going in. The other side, current coming out, yes, current coming out. From that, the flux distribution will be as shown. What I did here, I just inserted another tube around it and created some air gaps. If we look at the inner cylinder, the flux distribution, you find that the top half, the flux is going out of the surface. The bottom half, the flux is going into the surface. In other words, it will be something like this. I know this sketch looks very much, reminds me of the French flag, but the point I'm making is the top half will be magnetized in a direction opposite to the bottom half. That's north and south, and we only used one coil and two coil sides. The distribution of the magnetomotive force around the periphery of this structure will be as this. If you look somewhere here, there are no flux lines. Moving this way, clockwise, you will find the flux lines are going in one direction. Yes. Then you reach this point here, it goes down to 0. This is the other coil side. Beyond this point, you find that the flux is pointing the opposite direction. Yes, it's opposite direction. This point, of course, this point here, it's this one there. We just went around the circle. So let me remove this annotation. Now, this is the magnetomotive force and flux density distribution, and this will have a first fundamental and harmonics. Of course, if it's a wave as shown in the solid black, it will have high content of harmonics. How we need to reduce that, so we need to play a bit with the shape of this waveform. And what do we do? Well, here in this case, we considered 3 coil sides. And here you will find the flux lines as shown. Different situations now. You can see flux line, the flux line indicated by A has the magnetomotive force, the current, the total current enclosed by the flux line shown by A is 1 current. B and C enclose 1, 2, 3. If you look around, all the current enclosed by B and C is 3. So you end up with a distribution of the magnetomotive force. FA is 1/3 of FB and FC. You end up with a stepped waveform like this one. Stepped waveform like this one would have a fundamental and the harmonics, but of course the harmonic content will be better than, well, will be less high order harmonics than the just one step square wave. Anyway, by certain design techniques, it's possible to obtain MMF distribution which is very close to sine wave. So close, in fact, that it's a common practice that we assume it's sinusoidal distribution. We will deal with such winding arrangements when we considering special machines. All what I wanted to do in this presentation is to start with Amperes Circuit Law, very simple, that you all remember or should know from physics, or if you didn't remember it anyway, I revised it today. And from that, we moved into magnetic circuits and started modifying the magnetic circuits a bit, and then we found the construction of laminations in machines, and then we decided to distribute the winding, and we found that we can distribute the winding in slots. These slots can be either on the rotor and the inner cylinder or the outer cylinder. And we will discuss this in details later. So later on, when we discuss AC machines, and I start by using the number of ampere turns or coils and currents in slots, and I adjust them to give me a waveform that is sinusoidal, you know that I'm trying to get MMF that is sinusoidal, because as we'll see later on, if the flux density distribution is near sinusoidal, then the voltages induced will be sinusoidal. We'll discuss this in the next, not the following, but the next presentations. We'll talk to you then. Hello, this is part 3 of the series dealing with electric machines fundamentals. And in this part, we introduce the concept of rotating magnetic field. And all what I'm assuming that you know is that when we have a coil, when the current is going in, coming out, this coil carrying current will produce a magnetic field. We can determine the direction of the magnetic field using the right-hand rule. So the magnetic field during to the current shown in this red coil will be in the direction shown. And I'm assuming here that this current has a value, say 2 ampere. Now we are going to introduce another coil, the yellow coil. I don't think it's very clear, but you can see the X, current going in, current coming out. You apply the right-hand rule, the direction of the magnetic field will be in like that, pointing downwards. But I'm going to assume that the current in this yellow coil is half that of the red. So if the red current was 2 amp, the yellow current is 1 amp. So I'll end up with this value of the magnetic field. Then we add a third coil, the blue coil. The blue coil, current in, current out. So clearly the flux due to this current in, out, during applying the right-hand rule will be in this direction. The current magnitude again is the same like the yellow, half the red. It will give this blue magnetic field. The resultant magnetic field due to this combination of 3 coils which are displaced in space is to add the red plus the yellow plus the blue. You end up with this resultant magnetic field. Now we consider a case when the current values have changed. Now remember, the position in space will remain the same, the current values will change. And this is demonstrated here. The red current now will be 1 amp. So that's the flux due to the red current, which is 1 amp. The blue current is still 1 amp. Yeah, so that's the direction. But the yellow current increased to 2 amps. So that's the yellow field, twice the length of either blue or red. Add these 3 vectors together, you end up with the resultant component. You can see now that the resultant component has moved. It was at theta equals 0, now it moved clockwise to this position as a result of the changes of the magnitude of the excitation current in the 3 coil. This can be illustrated in the next slide with some animation. And here you can see the 3 coils, that's the red, the blue, and the yellow. First of all, at theta equals 0, the blue and yellow currents are equal and in one direction. So that's the yellow and the blue and yellow fields are equal in magnitude. The red current is twice the magnitude, so it's that. Add the 3 vectors together, you end up with the resultant magnetic field. What is shown here in the solid lines is the effective, this combination of currents. The blue and yellow act like a coil, although actually they are coil sides belonging to different coils. They act because the current is the same, so that's current in, current out produces field in this direction. Red current in, current out produces again horizontal direction, and then here the yellow current in, the blue current out, which are equal in magnitude, that will produce again field in this direction. So at theta or omega t equals 0, the current values are as shown, the distribution shown, and the resultant field is horizontal. Now we allow the time to progress and the currents to change here and see what happens. At this position, this is 30 degrees. This position here, you can see that the blue current is 0. Yes, the blue current is 0 and there is no magnetic field due to the blue winding. The red is this value, the yellow is the other value in different direction. So the red and yellow produce magnetic fields which are equal. Add them up, you end up with the black resultant magnetic field. It moved in space. If we move on another 30 degrees, we reach the situation shown here at omega t equals 60 electrical degrees. The red and blue currents are the same value, and you get the red and blue will produce magnetic fields that are equal. The yellow is twice the magnitude, and you get, add the three vectors up, you get the resultant field. Note now that the current in the blue coil has reverse direction. The blue coil, when we started, it was in, out, and the blue field was going upwards, well, going at opposite what's shown now. So I will keep this animation running, and you can observe it, and you can pause the recording at any point to check that the values of the current from the sinusoidal distribution of the current matches what you expect to see in the distribution of the field. So I'll keep it running now. You can check that when the current in any coil reaches 0, the field produced by that particular coil will vanish, and after that you will see that the direction of the field will reverse for that coil. All the time when you add the three magnetic fields together, you end up with a rotating resultant component, the black component here, that is rotating in space. Of course, all this can be proven mathematically, and what we're giving here is IA, these are just mathematical representation of the figure shown in the previous slide. This is the magnetomotive force for each current, and then you add them together, and bearing in mind that the magnetomotive force are also displaced in space with respect of each other by 120 degrees, or 2 pi over 3. You end up, when you add and simplify and use all the relevant equation, you end up with the resultant field that is equal to 1.5 the peak of any of the individual phase or winding fields, and it's rotating at a speed omega. That's actually electrical radian per seconds. So all what I want you to know for now is that if I have a 3-phase winding displaced by 120 degrees in space, excited with 3-phase balanced voltages V1, V2, V3, and they are equal, and again 120 degrees electrical between them. This plus that will give me a field that is rotating with a speed omega equals 2 pi f and that's electric radian per second. The relationship between electrical degrees and the mechanical degrees is actually what you measure, degrees, is that the electrical degrees is multiplied by the pole pairs, the number of the pole pairs of any device. I will use 2p equals number of poles, so p will be pole pairs. That's the notation I'm following in all this presentation and all the course. So if omega electrical is 2 by f, then you can easily find that the synchronous, this is omega s, and then you can find that the rotational speed in revs per minute, we call it synchronous speed, is 60 f over p, where p are the pole pairs. If you forget, and this is revs per minute, if you forget, some books says 120 f over p. Why? Their notation here is this number of poles, not pole pairs. So if you forget or get confused, remember something. 50 hertz, four poles gives a synchronous speed of 1500 revs per minute. So 60 multiplied by 50 is 300, 4 poles, so that's 2 pole pairs divided by 2 is 1500. So that's all what I want you to remember, and this will be my starting point when we start the presentation or the lecture on the induction motor. I will start with having a three-phase winding, balanced three-phase winding, supplied by a balanced three-phase supply. Their effect is to produce a rotating magnetic field. From then on, we'll just forget about all this and we will look at the effect of this magnetic field. So I'll see you next time. Hello again. This is the fourth part in which we are dealing with electric machine fundamentals, and in this part we will discuss the generation of electromotive force, EMF or voltage. And we start by defining Faraday's law. Michael Faraday, in the mid-1800s, he observed, he was one of those who knew that current carrying conductors, i.e. conductors with current in them, either repel or attract, i.e. they behave like magnets. So Faraday started a series of experiments, been working long time, to see if from magnets he can produce current, i.e. if current can behave like a magnet when it's in a coil, so why not a magnet can produce a current. The breakthrough came once when he moved a magnet to cut the turns of a coil, and the voltage was produced. And since then we know Faraday's law, and this is the only law that we will use. We will derive it in different format later, but Faraday's law states that the EMF, the voltage induced in a circuit, is equal to the rate of change of flux linking that circuit. Lambda here is flux linkage in vapor per turn. And what we can do is we consider a coil like this one, and then what is that lambda? We defined it actually in one of the earlier presentation in the series, but if all the flux lines were linking all the coil turns, then the flux linkage will be n turns of the coil multiplied by the flux phi. Generally, this is not the case. As we see here, the first turn, this turn, is linked only by 4 flux lines. Similarly, this one, and the middle turn is linked by 6 flux lines. So lambda in this case is 14. And if you wish to define an effective value of the flux that when multiplied by the number of turns of the coil will give you the flux linkage, you will get the effective turn is lambda over n, which is 14 over 3 vapor in this particular case. And in some books you will find that they use n d phi by dt. They're just assuming that all the coil turns are linked by the same number of flux lines, phi. Now, you remember the right-hand rule? If the current is as shown in red, i.e. like the fingers, so the flux lines will be going upward in the center of the coil, going around. So this is just a reminder of the directional relationship between current and the flux. And of course, if the current was in a long coil going like the thumb, then the flux lines will be circles around that conductor. If d lambda by dt what generates E, then it's not essential that the flux is produced by the coil itself. This coil shown here, of course there will be an EMF if the flux, this flux phi changes, there will be an EMF induced in this coil itself. However, if I bring another coil and I put it in the proximity of the first coil, the red coil will be cut by the flux lines, so the flux could be external to the coil. The change of flux or flux linkage can be either by changing the current or by changing the magnetic circuit configuration. Why? Because if you remember from the magnetic part earlier in this series, we found that phi is the magnetomotive force Ni over the reluctance R. This reluctance is L over mu A. This is the length of the flux path, and this is the cross-section area perpendicular to the flux lines, and I is the current of the coil. So you can change the geometry, A or L, or you can change I, and that will produce change of phi and the flux linkage. Also, if you look at this red coil here, if I keep moving this coil closer to the flux line and away from the flux lines like this, that flux linkage of that coil will change. So it can, flux linkage changes can also be produced by the change of position of the coil. And of course, it can be produced by simultaneous action, i.e. the coil is moving, but the coil itself is carrying current that is changing with time. So it's a combination between the first and second mechanism of change of flux. First, we consider the case when the voltage is produced or induced in a coil that is excited by a current. So we have a magnetic core here, and around it we want a coil, which is the blue coil carrying current I. The flux lines, if you apply the right-hand rule, will be like shown in red. Now, if the current, I assume that the current is sinusoidal, i.e. it's I maximum sine omega t. We know that phi is Ni over the reluctance of the circuit, and it will be N over R multiplied by I maximum sine omega t. In other words, if the current is sinusoidal, then the flux will also be sinusoidal. This is maximum, call it phi maximum. So what we can conclude from that is, if the current is changing sinusoidally, then the flux and the flux linkage will also be a sinusoidal waveform in phase with the current. And that's what we have here. The current is sinusoidal, and the flux, when the flux lines, the current as shown in this blue arrow, the flux lines will be like shown in red, so it will be as shown in this half cycle. At this point, just for simplicity, I will also sketch here the current I. The current I will behave like this. At this point, the current becomes 0, and of course the flux becomes 0. Then the current will reverse its direction as shown in green, and the flux lines will change their direction, and we get the other half, which means the flux linkage and the flux will be a sine wave, which is the same sine wave, has the same phase as that of the current, and the EMF differentiate this red equation of lambda. You end up with this, which this is, we can call this E maximum value. It's a cosine, and if you plot, you will find that lambda is shown and the EMF is shown. If in phasors, if we can say this is lambda, E will be another length of vector, but it's 90 degrees. So the EMF produced in this case is at right angle with the flux linkage. We look at salient structure like in machines. We have here a pole south and north, and if you remember, we defined, and as the convention is, if the flux coming out of a surface, we call that surface a north pole. If it's going into a surface, we call it a south pole. So we have south, north, north, south here. Have a brown coil, and this coil now is linked by a flux phi upwards. If I move this coil to this position, the coil is linked in a flux phi in the opposite direction. So the net change of flux, delta phi, is phi minus phi will be 2 phi. And if that happened in a time delta t, that will give you the EMF. So now the magnets are produced by a direct current. The flux is not changing with respect to time, but the position of the coil is changing, and we're moving it with certain speed. So this is the speed voltage. You would be familiar with another form of this equation, and now we will derive it using the same equation of Faraday, E equals d lambda by dt. To do this, I'm assuming that there is a flux density B in blue here pointing downwards, and I have a coil. This is the coil side, another coil side, and the end connection between the coil, what's shown here in green, I'm considering it an elastic connection. So if it is an elastic connection, in this position here, the flux linking this brown coil, phi, is B multiplied by the area. So it's B multiplied by X, the width here, multiplied by L, which is the length of the coil. Now, this side of the coil, the right-hand side, will move. It's an elastic connection, so you can see it's stretched a bit here. It's moved delta X, so the flux now will be, in this position, will be BL multiplied by X plus delta X. The change of flux between position 1 and position 2 will give you our flux linkage, delta lambda, BL delta X, and find E as d lambda by dt. So divide this equation by delta t, you end up BL dx by dt. dx by dt is the velocity v. The thing to note here is that the flux is perpendicular to the plane of the coil. So there is 90 degrees between B and L, and also the velocity V, and that's L. If you're studying physics, they will give you flux at certain angle, and then you will need to find that the normal component will produce EMF, the tangential component is not going to produce EMF. The main thing to note is, in electric machines, we will ensure that B, L, and V are at right angle with respect to each other, and the EMF induced will be given by the product. It is very important that you understand that we arrived at this expression BLV, which you would know from physics, by application of Faraday's law. It's not a new relationship or not new law. All what we did here is we just expressed the flux linkage in terms of the flux density B and the velocity at which the coil is moving. Now we look at a typical machine arrangement. This is a machine winding, and we have the coil shown in the first position. This is the position 1, and in the dotted line is position 2, and the flux density is B1 this side, B2 the other side. If we apply E equals BLV, assuming right angles between flux density, the conductor, and the speed at which the conductor is moving, you have the EMF generated at the coil terminal, the EMF as the coil moves from position 1 to position 2 is B1LV plus B2LV. What we do in machines is we arrange that when one coil side, like this one, is under, let's say, this is the North Pole, the other coil side is under a South Pole. So B1 and B2 are equal in magnitude, but they are opposite in sign. So what we get here, B1 magnitude equal minus the magnitude of B2 equals B. Substitute in this equation, the total EMF in the coil will be 2BLV. So although the EMF directions is reversed because of the reversal of the flux, when they add up, if you have EMF in this side acting like that, EMF on that side acting like that, around the coil they add up to 2BLV. Observation. EMF generation is not just associated with generator. EMF E will be produced in any circuit that is linked by a flux that is changing with time. So whenever there is change of flux linked the coil or the circuit, there will be EMF. So this EMF is also produced, generated in the motor, but in the motor we normally refer to it as the back EMF. Why back EMF? Because it opposes the flow of the current into the motor. We will come to that in more detail when we discuss specific motor topologies. See you next time.